Good afternoon, everyone. Yeah, I'm Yiyao from the Department of Chemistry. Currently, I'm a research assistant in Professor Zhang Hua's group. And thank you. Okay. Okay, that's going back. Okay, thank you very much. Thank you for the precious opportunity for us to share our recent progress of our research. Today, I will talk about some work about this research topic. It's phase engineering of palladium-based nanomaterials. Here, PD is one of the noble metal elements, which is short for the palladium. Okay, I will start my talk by introducing the background. Okay, first, I know that noble metal nanomaterials, including the silver, gold, palladium, platinum, and something else, have been extensively studied because of their promising applications in many fields, including the clean energy field as we're concerned. Especially, the noble metals can be used as a highly efficient catalysis in many catalytic applications, including the electric devices. Here, I show some examples for the typical electrocatalytic reactions. For example, the water splitting, which can be used to produce the hydrogen and the oxygen in a very green way. And also in recent years, the electrocatalytic CO2 reduction has also attracted increasing attention because it can efficiently feed the CO2 gas into the valuable fuels or valuable chemicals here. And as shown in this typical material science diagram, we know that the structure of materials can determine its property and the functions. So the structural modulation of the noble metal nanomaterial has been well studied in the past tens of years. The structures of nanomaterial of noble metals have been tuned to enhance their property by turning the shape, the size, the dimension, or the facets of them. Besides these structural factors, the phase of nanomaterials have also been revealed to play a key role in determining their properties. Here, the phase means the atomic arrangement of the materials. So our group has proposed a new strategy, which is the phase engineering of nanomaterials, to turn the phase of nanomaterials for modulating their functions. As a result, many nanomaterials with unconventional physics that are different from the thermodynamic stable ones in the bulk forms have been discovered or prepared. Typically, we can divide the unconventional phase into three parts. The amorphous one with disordered, long-range disordered structure, or the unconventional crystalline phase different from the thermodynamic stable ones, or the unique hyperphase, which is composed of two or more different phases here. And when we focus on the phase engineering of noble metals, we can see here, noble metals normally crystallize in closed-packed structure. Most of them are in the phase-centered cubic, which is FCC phase, and some of them are in HCP phase. But up to now, turning the phase in noble metals is still very challenging because of the metastable nature of the unconventional physics here. Here, I will show some typical examples of the unconventional phase noble metal nanomaterials by using gold as an example. Actually, the phase engineering of gold nanomaterials has been well studied in the past maybe 10 years. So many gold nanomaterials with the unconventional non-FCC phase have been synthesized. Actually, our group have also devoted great efforts into this field. For example, back to 2 years ago, we have synthesized the gold nanosheets with a square-like shape and also a HCP 2H phase for the first time. And later, our group have stabilized another HCP phase, the 4H phase, into the gold nanoribbons, and followed by the report on the gold nanorods with a hyperphase, which is the alternating stacking of 4H and FCP phase. And also the report on the hyperphase gold nanorod with a very well-defined sandwich-like structure, FCP2H, FCP hyperphase structure. We also investigated the phase-dependent catalytic performance of these gold nanomaterials for some applications. For example, here we use CO2 reduction as a typical example. We can find that the gold nanomaterials with the unconventional physics, such as this hyperphase structure or the 4H nanoribbon structure, they do show better catalytic performance compared to the conventional FCC gold. So this work demonstrated that the phase is really important for the enhancing of their catalytic performance. But apart from gold, when we talk about the phase engineering of other noble metals, such as the PD, PT, rhodium, or iridium, we found that the phase engineering of these metals have been seldom realized, especially for the PD-based nanomaterials, which is stable in conventional FCC phase. Actually, PD-based nanomaterials have been widely used for highly efficient catalysis for tens of years, and their structure modulation has been well studied. So the PD nanomaterial with a lot of shapes and exposed facets has been prepared. But almost all the previous works only focus on the conventional phase, which is the FCC phase. So to the best of our knowledge, we listed very few of the previous study which has succeeded in preparing unconventional phase PD. For example, in 2008, this work reported the synthesis of PD box with the FCT phase by the high pressure compression of the FCT PD nanotubes and very high pressure about 25 GPa. Then the FCC lattice will be distorted into the FCT phase. Our group also demonstrated another way, the seeded epitaxial growth route to synthesize the unconventional phase shell. For example, the 4H FCC hyperphase PD shell can be epitaxially grown on the surface of the 4H FCC gold nanorod as a core. So, and we also demonstrated that this 4H FCC PD nanostructure can show a better ethanol oxidation performance than the conventional FCC PD. Based on the aforementioned background, we have set our research object. We like to develop new synthetic route to achieve the controlled synthesis of more unconventional phase PD nanomaterials and also the PD-based heterostructure. But how to achieve this? Evidence there by some other previous studies in the metal compounds, we have proposed an idea. Because the previous study shows that when during the crystallization of the amorphous structure to the final thermodynamic stable crystal phase, there might be some metastable crystal phase showing up during this transformation process. So we proposed an indirect route to synthesize unconventional phase PD by the controlled crystallization of amorphous PD. But in this synthetic route, there are two key challenges existing. The first one is that the synthesis of amorphous PD nanomaterials itself is very difficult because the strong metallic bond between PD atoms, so it tends to form a crystalline structure. And the second difficulty is that we need to pressure control the crystallization kinetics of this amorphous PD during this transformation process to maintain the metastable structure. Okay, I will show our result about this controlled synthesis of PD nanomaterials. By following the aforementioned strategy, here we first developed a wet chemical reduction method to prepare amorphous PD nanoparticles as a starting materials. As schematically shown here, we use oleamine as both the solvent and the reductant, and use a can of soil molecules as a unique surfactant, which is very important for the formation of amorphous PD. As a result, we have successfully synthesized the monodispersed PD nanoparticles with a sphere-like shape and also the totally disordered atomic arrangement. And also our SRD result shows no diffraction peaks, confirm the amorphous phase of these PD nanoparticles. Subsequently, we conduct the heat treatment for these amorphous nanoparticles. And we found that by changing the experimental condition, we can realize different crystallization routes for these amorphous PD. For example, when we're heating the amorphous PD in oleamine solution under an air atmosphere, we found that monodispersed PD nanoparticle with a conventional FCC phase was obtained, which is confirmed by our characterization. Very interestingly, if we change the heating experimental condition, which is heating it under high vacuum condition, we can realize another route of crystallization to obtain PD nanoparticles with an unconventional 2H crystal phase. And our crystallization also confirms the novel 2H phase of the PD nanoparticles. We can observe the AB repeating stacking of the typical 2H phase. And we further compare the detailed structure of the FCC and the 2H phase PD nanoparticles. In the SRD characterization, we can observe the totally different diffraction peaks for these two samples, which are all matched well with the simulated theoretical ones. And this can prove their high security and also their totally different atomic arrangements. And also we unraveled that the FCC-PD and the 2H-PD both show very similar nanosemic substatus compared with the PD foil, so confirming their metallic strip. Here, we assumed that the different crystallization route of amorphous PD under the different heating conditions is attributed to the different crystallization kinetics. For example, when we're heating the amorphous PD in air, which is the route 1, the sulfur content ligand on the surface of amorphous PD will be rapidly oxidized and dissolved from the surface, so which lead to the fast crystallization to form the thermodynamically stable FCC phase. And when we're heating them and the vacuum, the sulfur content ligand will keep kept on the surface of amorphous PD during the heating. So it will lead to a slow crystallization, crystallization rate, which may be responsible for the formation of 2H phase. That's our hypothesis. And also we further compared the property and the application performance of these two PD nanoparticles with different physics. Here we show some data about the catalytic activity towards the ethanol oxidation reaction. Here we can see that the 2H-PD do have a much better catalytic activity than the FCC one, especially the specific activity is much higher than the FCC one, indicating it has a higher intrinsic activity. So after the successful synthesis of 2H-PD nanocrystals, we further moved to the phase engineering of PD-based multimetallic cathode structures. As I mentioned before, the speed-mediated epitaxial growth is a very efficient way to generate an unconventional phase metal shell on the surface of the metal core. Normally, the shell metal will strictly follow the lattice of the core metal to form the same unconventional phases. But here, when we use the 2H-PD as a seed to grow the other metals, we demonstrate another new epitaxial growth mode, which is a phase-selective epitaxial growth. Here, we use gold as an example. When we grow gold on the surface of PD, we can observe the formation of core-shell nanorods. Here, from this CHEM image, we can clearly distinguish the PD core with the darker contrast in the middle part, and the gold shell with the bright contrast outside. And more interestingly, the gold shell is in FCC2H, FCC sandwich-like heterophase structure. The characterization can confirm the selective epitaxial growth of FCC gold on the 2002 facets of this 2H-PD. And also in the middle part, 2H gold was formed on other facets of PD in this middle part, so forming this sandwich-like structure. And such unique phase-selective epitaxial growth is attributed to the structure match between the 002 plan of 2-HPD and the 111 plan of FCC Gold. Here we can see in these schemes, the 002 plan of 2-HPD and the 111 plan of FCC Gold are both the closed packed structure in the noble metals, which show the same six-fold symmetry and a very similar lattice parameter as we showed here. So this good structure match between these two facets will lead to the formation of thermodynamic stable FCC gold on the 002 plane of 2-HPD along the closed path direction to form such a sandwich-like heterophase structure. So we further studied the kinetic performance of this kind of heterophase covalent nanorods. We use the CO2 reduction as a typical example. We found this nanorod can show very good CO2 reduction performance with a high CO efficiency among a very wide operation potential window, and it can outperform the FCC PD gold covalent nanoparticles and also the FCC gold nanorod with a similar morphology, which means the crystal phase is very important here. We also use a theoretical study to confirm this point. We found that this unconventional 2-HPD gold structure and the 2-HFCC phase boundary can show a lower energy barrier for the CO2 reduction and a higher energy barrier for the competing hydrogen evolution. So this means the heterophase structure and the covalent structure both contribute to this highly efficient CO2R. And we further demonstrated that this phase-selective epitaxial growth can be used as a general method to synthesize different PD-based covalent structure with similar FCC2H FCC heterophase. But the morphology can be done. For example, here we show the characterization of a PD silver covalent nanoplate. And also we can obtain this PD-PT covalent nanoparticles with similar FCC2H FCC heterophase structure and similar PD iridium covalent nanostructure. This one is quite interesting because when we growing more iridium on the surface of 2-HPD, we can observe the formation of both FCC and the 2H iridium branches to form such kind of multi-branched dendrite-like morphology. So these PD iridium covalent nanodendrites can be used as HER catalyzed for a very low over potential of only 11 millivolts, and it can outperform the FCC PD iridium covalent nanostructure and also the commercial catalyzed here. Recently, we also demonstrated another kind of epitaxial growth mode, which is static selective epitaxial growth. We can achieve the selective growth of two triangular rhodium nanoplates on the 2002 facets of 2-HPD to form such kind of 2D on 0D PD rhodium hierarchical halo structure. Actually, this structure is quite unique and uniform. And this hierarchical halo structure can also be used for HER with a very good performance. It can outperform the FCC PD rhodium covalent nanomaterials with a similar composition. Further, we developed another seeded diffusion synthesis method to synthesize different 2H-based PD-based alloys through the wet chemical reduction of second metal and the following thermal diffusion of them. And also by using a galvanic replacement reaction, we can further synthesize trimetallic alloys with 2H-base. Here is the characterization of our 2H-based PD copper nanocrystals with the tunable copper content and also the 2H trimetallic PD copper alloy. These kind of PD-based alloy can be used for the electrocatalytic oxygen reduction. We found that even with the similar morphology and the similar composition, our 2H-based PD copper can show a better performance than the conventional FCC alloy. Yes, and also after the doping of PD, it can show a high OR method activity and also good catalytic stability here. Okay, as a brief summary, In this research direction, we designed a new synthetic structure, which is a controlled crystallization of amorphous structure for the phase-tunable preparation of PD nanomaterials, especially the nanomaterials with unconventional phases. And also, we demonstrated some new architectural growth move when we growing metals on the 2H-PD nanosheet, including the phase selective and the facet selective embedment growth. For the construction of some novel PD-based halo structure. We also developed a new feeded diffusion method for interface of some 2H-based PD-based nanoalloys. And we further studied the phase-dependent performance of these PD-based nanomaterials for many different catalytic reactions. And we demonstrated that these unconventional phases can indulge the PD-based nanomaterials with enhanced catalytic performance, which means this unconventional phase is quite important here. And based on our current research, we will keep devoting more efforts to the exploration of more unconventional phase materials for other applications by following our strategy of the phase engineering of nanomaterials. Okay, that's all for my presentation today. So thank you for